Hello, my name is Matthew Tilmowitz, and this is my Week 10 document classification assignment. So for this assignment, we were tasked with going through a corpus of documents and labeling them ham or spam. We used the spam-based dataset from UC Irvine. The dataset is 4,601 emails that have been labeled with 57 pre-computed features. The underlying documents weren't part of the dataset, which was kind of unfortunate. It would have been interesting to, generate some embeddings with a model like Roberta or other common models and see whether these model-generated embeddings improved upon the hand-engineered features, but unfortunately, we cannot do that. As the study already defines the features, defines the distributions, the ranges, and indicates that there's no missing values, we're not going to be doing any exploratory data analysis as it's already well established and it lives in the same place as the data set. We will be evaluating logistic regression, random forest, AdaBoost, and neural network models. They cover a diverse range of model classes, with logistic regression acting as our baseline, random forest and AdaBoost, different approaches to ensemble tree models, particular with AdaBoost using the boosting mechanism, and then the neural network is obviously its own class of model. The original study made use of 3 of these model types as baselines, so we will be comparing our performance with those baselines. And we noticed during training, many of these models were able to achieve an OCROC in excess of 0.99, indicating that they were kind of getting saturated in terms of their ability to learn from the dataset. So we will be using average precision for our model training and selection. This is because average precision in particular is a very useful metric on imbalanced data sets. Although this data set in particular is not highly imbalanced, it'll be interesting to explore whether or not this affects model performance meaningfully compared to those baseline models. So we're not just rehashing the exact same project that was already done. Column names are provided by the dataset already, and then just validating that our dataset that we loaded in matches that of what we would expect it to be. So we split the data into 3 splits, the train, validate, and test split, as is best practice. The test split contained 20% of the data. The validation set consisted of 16% of the data, which is 20% of the remaining data. We used stratified sampling to ensure that the class imbalance is consistent across all splits. And then we centered and scaled the values using the robust scaler, which is very resilient to outliers due to using median and interquartile range instead of mean and variance in its normalization, which generally leads to better performance by models. Logistic regression acted as our baseline. We evaluated different penalty methods such as lasso, ridge, and elastic net. The best performing model was simple ridge regression and achieved an average precision of 0.9 on the validation set. For the random forest model, after hyperparameter tuning, we were able to achieve a average precision of 0.98. Also, it should be noted we did 5-fold cross-validation for all of these models. The AdaBoost model also performed very well, achieving 0.97, very close to that of the random forest model. And finally, the neural network, we tuned across a variety of hyperparameter sizes and layers, although we were, of course, limited by the available compute and the time it takes to train neural networks. We experimented with 2 hidden layer networks with differing dimension sizes per layer. And then we also experimented with a 3-layer neural network, 3-hidden layer neural network. We evaluated different dropout values as well as learning rates to provide a reasonable spread of values. The models were all trained over a maximum of 100 epochs with early stopping implemented. All models did end up stopping early, indicating they had reached convergence. The best performing model was the 3-layer model with a relatively high dropout rate and achieved an average precision of 0.96. It would be interesting with more compute resources to evaluate, even deeper networks to see if the model is able to continue to learn, given that there's a relatively small feature space originally, which is kind of surprising that the deepest network was actually able to generate more information. Evaluating the models on the test set, we looked at a wider range of values. We obviously included accuracy, precision, recall, F1 score, and average precision. And very interestingly, the models fell into a very distinct stratification, with the random forest model performing best by every metric, followed by the AdaBoost, the neural network, and the logistic regression models. It's really unusual for models to, a single model to perform best by all metrics that are included in this comparison, let alone for all models to fall into such a distinct hierarchy. It's very, very rare for that to happen, and is particularly interesting. It appears that the model architecture of random forest is by far the best performing across all metrics. Although it should be noted, the random forest and neural network models both outperformed on the test set as opposed to the validation set, indicating that they both generalize really, really well to the problem space. All models performed remarkably well, achieving values in excess of 0.9 by virtually all metrics except for the logistic regression model, which is remarkably good performance in general, indicating that these handcrafted features were very, very informative and very, very appropriate for the problem at hand. Looking at these models compared to the baselines in the included with the dataset, we can see that our logistic regression model actually underperforms. We can bring this down and take a look at the values. So our logistic regression model underperformed, which we define as falling outside of the range of values exhibited for each model type. Our neural network outperformed, the random forest model matched, and then comparing the AdaBoost to the XGBoost, as they both use gradient boosting algorithms, the AdaBoost model matches the XGBoost, they're just barely falling within the range, and that's consistent across both accuracy and precision as metrics. That is my presentation, and thank you for listening.